lecture on the subject Computer Vision, Unit 4, 3D Construction, Part 2. I am Dr. K. Padmapriya, Assistant Professor, Department of ECE, Government College of Engineering, Tirunelveli. Active range finding. So this is the diagram which shows the range data scanning. So a laser dot on a surface which is imaged as a CCD sensor, and this is the surface, and a CCD captures the image at this position, that is the point of view. And a laser stripe sheet which is imaged by the sensor and which is capturing the image of this object when the light falls over it, and this is the direction of the travel. So the recorded images will be captured with the CCD, and the part C and D are the resulting set of 3D points which are turned into a triangular mesh in D. Active range finding. Actively lighting a scene, whether for the purpose of estimating normals using photometric stereo or for adding artificial texture for shape from defocus, can greatly improve the performance of vision systems. This kind of active illumination has been used from the earliest days of machine vision to construct highly precise sensors for estimating 3D depth images using a variety of range finding or range sensing techniques. While rangefinders such as LIDAR, that is the abbreviation of light detecting and ranging, and laser-based 3D scanners were once limited to commercial and laboratory applications. The development of low-cost depth cameras such as Microsoft Kinect have revolutionized many aspects of computer vision. It is now common to refer to the registered color and depth frames produced by such cameras as RGB-D or RGB-D images. One of the early active illumination sensors used in computer vision and computer graphics was a laser or light stripe sensor, which sweeps a plane of light across the scene or object while observing it from an offset viewpoint. As the stripe falls across the object, it deforms its shape according to the shape of the surface it is illuminating. It is then a simple matter of using optical triangulation to estimate the 3D locations of all the points seen in a particular stripe. Knowledge of the 3D plane equation of the light stripe allows us to infer the 3D location corresponding to each illuminated pixel. The accuracy of light striping techniques can be improved by finding the exact temporal peak in illumination for each pixel. And this picture shows the shape scanning using the cast shadows. And this is the camera setup with the point light source and the camera to capture the picture. The objects being scanned in front of two planar backgrounds, and the real time depth map will be use a pulsed illumination system. Very fast scanners can also be constructed with a single laser beam, that is a real-time flying spot optical triangulation scanner. Instead of projecting a grid, it is also possible to project one or more sinusoidal fringe patterns and to then recover deformations in the surface from the relative phase displacements using a process called fringe projection profilometry. The Microsoft Kinect depth camera uses a variant of this technique, projecting an infrared speckle pattern, which looks like a bunch of random dots, but which in fact consists of a known calibrated pseudo-random pattern. And this has been shown in the next picture. By measuring the horizontal displacement, that is called as the parallax, between the dots seen in the IR camera and their expected locations, a depth map can be computed interpolating over the pixels not illuminated by the dots. So Kinet camera has been widely used in applications such as 3D body tracking. This is the Microsoft Kinet depth camera, the hardware, which comprises an IR speckle and IR projector, RGB camera and IR cameras. So all these comprises the Microsoft Kinet depth camera. It has a color and IR camera pair. So both RGB camera and IR camera both are pair, which is present behind here besides the infrared projector. So close-up of a sample infrared image is shown in B, and the C part is the final depth map, which has black shadows in the areas which are not illuminated by the projector. Instead of using a single camera, it is also possible to construct an active illumination range sensor using stereo imaging setups, resulting in a system that is often called active illumination stereo. The simplest way is to just project the random stripe patterns onto the scene to create synthetic texture, which helps match textureless surfaces. Caution about active range sensing. When the surface is being scanned or too reflective, the camera may see a reflection of the object surface and assume that this virtual image is the true scene. For surfaces with moderate amounts of reflection, there is still sufficient diffuse reflection under the specular layer to obtain a 3D range map. The specular part can be recovered separately to produce a surface light field. For true mirrors, the active range scanners will invariably capture the virtual 3D model seen reflected in the mirror, so that the additional techniques such as looking for a reflection of the scanning device must be used. Range data merging. It means the registration alignment of the partial 3D surface models and their integration into coherent 3D surfaces. ICP, which means the abbreviation of iterated closest point, which alternates between finding the closest point matches between the two surfaces being aligned and then solving a 3D absolute orientation problem. The picture shows the range data merging. We have two signed distant functions, the topmost left, and that are merged with their weights. And this is the bottom left. Now it's merged with the weight, and then it produces a combined set of functions. So you get different functions of it, from which an iso surface can be extracted. So this is shown as the green dashed lines in between. So here you have the dashed line, and this is called as the iso surface. So this is unseen part, and this is the part which is visible to us. So it is empty. Now you can see the gaps in between what you have. So this is the whole fill iso surface. And signed distant functions are combined with the empty and unseen space labels to fill the holes in this iso surface. So the application of it is digital heritage. So it is used for restoring the historical places in digital manner. So laser range modeling of Dayon temple at Angkor Thom, and the first picture is about the sample photograph from the site, and the second one is a detailed head model scanned from the ground, and the third one is the final merged 3D model of the temple scanned using a laser range sensor mounted on a balloon. So active range finding technologies combined with the surface modeling and appearance modeling techniques. They are widely used in the fields of archaeological and historical preservation, which often also goes under the name digital heritage. In such application, detailed 3D models of cultural objects are acquired and later they are used for applications such as analysis, preservation, restoration, and the production of duplicate artwork. The digital Michelangelo project, the laser scan of the David, all those it uses the cyberware laser stripe scanners and high quality digital SLR cameras mounted on a large gantry to obtain detailed scans of Michelangelo's David and other sculptures in Florence. Surface representations. Different representations being used to integrate 3D range scans. Explicit surface representations such as triangle meshes, splines, and subdivision surfaces enable not only the creation of highly detailed models but also the processing operations. So the processing operations are surface interpolation, fairing or smoothing, and decimation and surface simplification, then geometric images. We also examine the discrete point-based representation and volumetric representations. So we can see one by one the processing operations which we use for surface representation. So the first one is surface interpolation. So surface interpolation is one of the most common operations on surfaces, which is the reconstruction from a set of sparse data constraints, that is scattered data interpolation. So when formulating such problems, surfaces may be parameterized as height fields f of x, as 3D parametric surfaces f of x, or as non-parametric models such as collections of triangles. To solve problems like discontinuities in the surface as well as local orientation constraints is to discretize both the surface and the energy on a discrete grid or mesh. They are using finite element analysis and they are using sparse system solving techniques such as multigrid or hierarchically preconditioned conjugate gradients. Using a hierarchical combination of multi-level B-splines and then they use radial basis or some kernel functions. So these are the four techniques they use to solve over this mesh. When a 3D parametric surface is being modeled, the vector valued function f encodes 3D coordinates x, y, z on the surface and the domain x equals s comma t encodes the surface parameterization. So one example of such surfaces are symmetry seeking parametric models which are elastically deformable versions of generalized cylinders. In these models, S is the parameter along the spline of the deformable tube and T is the parameter around the tube. A variety of smoothness and radial symmetry forces are used to constrain the model while it is fitted to image-based Silhouette curves. To define non-parametric surface models such as general triangulated meshes and to equip such meshes with both internal smoothness metrics and external data fitting metrics. While most of these approaches assume a standard elastic deformation model which uses quadratic internal smoothness terms, it is also possible to use sublinear energy models to better preserve surface creases or to use graph convolutional neural networks as an alternative to the update equations as in deep active surface models. Triangular meshes can also be augmented with either spline elements or subdivision surfaces to produce surfaces with better smoothness control. Both the parametric and non-parametric surface models assume that the topology of the surface is known and is fixed ahead of the time. For more flexible surface modeling, we can either represent the surface as a collection of oriented points or use 3D implicit functions. which can also be combined with elastic 3D surface models. The field of surface reconstruction from unorganized point samples continues to advance rapidly, with more recent work addressing issues with data imperfections. The second technique is surface simplification. Once a triangle mesh has been created from 3D data, it is often desirable to create a hierarchy of mesh models, for example, to control the displayed level of detail (LOD) in the computer graphics application. In essence, this is a 3D analog to image pyramids. One approach to doing this is to approximate a given mesh with one that has subdivision connectivity, over which a set of triangular wavelet coefficients can then be computed. A more continuous approach is to use sequential edge collapse operations to go from the original fine resolution mesh to a coarse base level mesh. The resulting progressive mesh representation can be used to render the 3D model at arbitrary levels of detail. The diagram shows the progressive mesh representation of an plane model. So the basic mesh M0 with 150 phases, and the next stage of developed mesh with M175 with 500 phases, and the third one is a mesh with M425 which shows 1000 phases, and the final one is the original mesh, that is M equals M power n, which has 13,546 phases. So as the number of phases increases, we can see the details of the picture have been increasing. The third technique is geometry images. While multi-resolution surface representations support level of detail operations, they still consist of an irregular collection of triangles, which makes them more difficult to compress and store in a catchy, efficient manner. To make the triangulation completely regular, uniform and gridded, describe how to create geometry images by cutting surface meshes along well-chosen lines and flattening the resulting representation into a square. And this figure, it shows the resulting XYZ values of the surface mesh mapped over the unit square. So this is the surface mesh which is matched over the unit square. So for each unit square, this has been overlapped. And the B part shows the associated normal maps, that is for the corresponding points x, y and z. The normals are nx, ny and nz. And the surface normals associated with each mesh vertex, which can be used to compensate for loss in visual fidelity if the original geometry image is heavily compressed. So this shows the geometry images. This is a 257 cross 257 geometry image, defines a mesh over the surface. And the next one is the normals of each point of x, y, z, that is nx plus ny plus nz. So the cumulatively it relates, after the cumulative operation, it leads to the final lit 3D model. So this is the normalized map which gives all the vertex normals. So when you add them up, we get the final model like this. Thank you. With the second part of the video of Unit 4 Computer Vision.